Kamiak Butte is a fascinating landmark located in eastern Washington state in a region known as the Palouse. Here, I'm going to discuss just a few of the many features that make it so unique. To explain what makes Kamiak so unique, it's necessary to explain its formation. To do so, we need to go back 100 million years ago to a time when Kamiak Butte was covered in ocean. The ground was covered in a sedimentary quartz sand that formed into sandstone and later quartzite. This quartzite is important as it forms the bottommost layer of the substrate at Kamiak Butte today. The outermost solid layer of the Earth is referred to as the lithosphere. Rather than one solid layer, it's broken up into uneven pieces called tectonic plates. These large plates move in response to activity deep in the core of the Earth below them. Subduction zones form along the edges of continents, such as where Kamiak Butte was located at this time. Here, denser oceanic plates move underneath land masses and are melted into the mantle and destroyed in a process called subduction. At the same rate, the land masses were expanding westward. By 50 million years ago, the land had expanded enough that Kamiak Butte was no longer underwater. The process of subduction creates pressure in the mantle until eventually it erupts onto the surface. This was also the case at Kamiak Butte between 14 and 17 million years ago, when the buildup of magma caused a massive eruption. At the same time, it formed a volcanic hotspot known as the Yellowstone Trend. As the lava hardened, it became what is known as the Columbia River flood basalts. This basalt covered 63,200 square miles of land and 40% of Washington state, including the Palouse. The Columbia River flood basalts are especially unique as they are the youngest flood basalt in the world. Kamiak Butte would be far taller today if it wasn't for those flood basalts. Only the very tip of Kamiak remains uncovered today. It's estimated that Kamiak Butte would be nearly 10,000 feet tall had it not been for the dense flood basalts that kept it at today's height of 3,641 feet. "11,700 years ago, the climate begins to warm and we start to see the end of our most recent ice age. As the glaciers melt, this water caused what's known as the Ice Age floods. Water followed river systems but overflowed, forming Glacial Lake Missoula. Eventually, the dam holding the water into Glacial Lake Missoula broke, causing repeated flooding cascades until it finally emptied into the Pacific. With each flood, Glacial Lake Missoula brought with it organic material like soil and debris that it left as mud at Wallula Gap. Marine polar winds transformed this material into silt and carried it to the Palouse, where it still remains today. This soil and silt mixture formed an extra fertile, nutrient-rich soil that's regarded as loess soils. Kamiak Butte is located within the Palouse, highlighted in green on this map. The Palouse is part of the North American Western Interior shrubland and woodlands biome. This biome has broad, large-scale characteristics like fractionated exposed soil, which water can easily move through, vegetation of both grasses, shrubs, and trees, and plant communities that compete for both water and space. The Palouse Prairie is a variation of this biome. The primary species of trees growing here are ponderosa pine, western juniper, Douglas fir, and western larch. Shrubs and grasses that natively thrive are sagebrush, saltbush, rabbitbrush, and bunchgrass. However, due to anthropogenic influences, very little of this native vegetation remains. The photo on the left here shows a rare example of what the Palouse Prairie should look like. As you can see, shrubs and grasses are abundant. However, this is vastly different from the photo on the right. Agriculture has dramatically changed the landscape of the Palouse Prairie, leaving less than 1% of the native Palouse Prairie remaining. The substrate in the Palouse makes it the ideal location for agriculture. Remember the loess soil mentioned earlier? This provides extra fertile soil that agricultural crops like wheat, barley, and lentils grow phenomenally in. The basalt layer underneath provides a nearly impermeable barrier to water. This keeps moisture in the soil, allowing the crops to grow well without the need for additional irrigation. However, Kamiak Butte lacks those flood basalts that are key for trapping moisture. Due to this, it's impossible to cultivate agriculture there. Any moisture washes quickly away as it moves through the quartzite layer underneath. Hence, Kamiak Butte can avoid agricultural influence and maintain more of its native vegetation. Another unique characteristic of Kamiak Butte is its microsite delineation. A microsite is a very small area that has a unique environment associated with characteristics such as precipitation, nutrients, soil makeup, humidity, and solar radiation. The northern and southern aspects of Kamiak Butte both form their own microsites due to the differing amounts of solar radiation received. Due to an increased elevation in the southern aspect, it receives a more direct angle of rays from the sun. As Kamiak Butte is in the southern hemisphere, the soil on the south aspect also receives more direct sun rays, increasing its insolation and thermal energy. This leads to more water being lost through transpiration and evaporation, resulting in an inherently drier climate. Thus, plants that can grow well on the southern aspect need to be adapted to drier soils and higher temperatures compared to the northern aspect. Furthermore, shade-tolerant plants such as ferns are only able to grow on the northern aspect where they can be protected from the intense sun rays. Using data collected from a virtual field trip, I completed a statistical analysis on the tree distribution for each aspect of Kamiak Butte. This table is specific to the northern aspect. Here, there are 130 trees and a basal area of over 270 feet per acre. Douglas fir predominate here, but western larch and ponderosa pine grow as well. As you can see here, the southern aspect is vastly different. There are significantly less trees per acre, at only 35, as well as a far smaller basal area. This supports the facts behind solar radiation in the southern aspect. Due to the decreased moisture, the plants must compete more to survive, and thus they grow much sparser. Ponderosa pines are also the only tree that's capable of surviving with this much solar radiation, so it's the only tree present. The last section of this presentation highlights one species native to the Palouse, the Shiras moose. The smallest of all moose species, it's also the largest mammal that calls Kamiak Butte home. The Shiras moose was named in 1914 by Edward W. Nelson. Nelson named the moose after his good friend George Shiras III, a U.S. representative and a respected nature photographer. Here is a video I took last year of a Shiras moose buck. This was filmed a few hours outside of Kamiak Butte, near Cheney, Washington. Shirasi moose are the only subspecies of moose present in the Palouse region, as their smaller size is adapted for a higher fitness for the warmer climates. Shirasi moose rely on mature forests in their habitat for shelter from predators. It is important that the forest that the Shirasi live in has snow, as this creates additional shelter from predators. Kamiak Butte is an example of this, as it has a higher elevation than the surrounding area in the Palouse and therefore retains snow longer. This allows Shirasi moose to be able to fill their niche at Kamiak Butte. Moose usually avoid people, so they can be difficult to find. Remote trail cameras installed on Kamiak Butte have greatly increased the sightings of Shirasi moose. Without trail cameras, it would be hard to confirm the presence and abundance of Shirasi moose. Ecologists would have to rely on shed antlers and droppings to identify if they were there. This photo was taken using a remote trail camera of Shirasi moose on Kamiak Butte in September of 2021.